When we look into the night sky, we are not simply looking across distance. We're looking back in time. Light takes time to travel, and the farther away an object is, the older the light we receive from it. Because the universe has a finite age, approximately 13.8 billion years, there's a limit to how far we can see. That limit defines what scientists call the observable universe. The observable universe is not the entire universe. It is a portion from which light has had enough time to reach us since the Big Bang. Due to cosmic expansion, this region extends far beyond 13.8 billion light years. In fact, because space itself has been stretching while light travels, the observable universe is about 93 billion light years in diameter. But here's a profound question. What lies beyond that boundary? The edge of the observable universe is not a physical wall. It is not a barrier or shell. It is simply the distance limit imposed by the age of the universe and the speed of light. Beyond it, there may be more galaxies, more stars, more cosmic structures, but their light has not yet reached us. If the universe is infinite, then beyond the observable horizon there are regions exactly like ours, perhaps containing galaxies arranged differently, perhaps even containing planets identical to Earth. In an infinite universe, every physically possible configuration of matter would eventually repeat somewhere. However, infinity is not the only possibility. The universe could be finite but unbounded, like the surface of a sphere extended into 3 dimensions. In such a geometry, traveling far enough in one direction might eventually bring you back to your starting point, although the scale required would be beyond comprehension. Modern cosmological observations suggest that on large scales, the universe is remarkably flat. Measurements of the cosmic microwave background indicate that space is not strongly curved. This supports the idea that the universe may extend far beyond what we can observe, possibly infinitely. But even if it is finite, its true size may be vastly larger than the observable portion. There is another layer to this question. During the earliest moments after the Big Bang, the universe underwent a phase known as cosmic inflation. In a tiny fraction of a second, space expanded exponentially. Inflation may have stretched the universe so dramatically that the observable region is only a small patch of a far larger reality. Some versions of inflation theory predict that inflation never fully stopped. Instead, different regions of space may have stopped inflating at different times, forming separate bubble universes. This leads to the concept of a multiverse, a vast collection of universes beyond our own observable region, each potentially with different physical constants. If this is correct, then beyond our observable universe may not simply be more the same. It could be entirely different domains of reality, governed by different laws of physics. However, we must be cautious. The multiverse remains speculative. It arises naturally from certain mathematical models, but direct evidence is lacking. The observable universe is the only region we can study directly. Still, the boundary itself is fascinating. The observable horizon is constantly changing. As time passes, light from more distant regions has time to reach us. The observable universe grows. At the same time, cosmic expansion is accelerating due to dark energy. This means that some distant galaxies are moving away from us so quickly that their light will never reach us in the future. They are receding beyond a different boundary known as the cosmic event horizon. So while the observable universe grows in some directions, parts of it are also becoming permanently unreachable. The universe is not just expanding, It is separating. To imagine what lies beyond the observable universe, we must confront the limits of physics and philosophy. If space is infinite and uniform on large scales, then beyond the observable horizon, there are more galaxies arranged in patterns similar to ours. There may be countless Milky Way-like galaxies. There may be Earth-like planets orbiting sun-like stars. There may even be regions where, purely by chance, atoms are arranged exactly as they are here, forming duplicates of you and me. This is not fantasy. In an infinite cosmos governed by finite combinations of particles, repetition becomes mathematically inevitable. Yet the universe might not be infinite. It could be finite, but extremely large. If so, its total size could be many times larger than what we observe, perhaps hundreds or thousands of times large in diameter. In that case, beyond our observable region would simply be more of the same cosmic structure, galaxies, voids, clusters, extending far beyond our horizon. But inflationary cosmology introduces stranger possibilities. If inflation created many disconnected regions, then beyond our observable universe might exist entirely separate universes with different physical constants. In some, gravity might be stronger. In others, atoms might not form. Some might expand too quickly for galaxies to develop. We cannot observe these regions directly because light from them cannot reach us. They are beyond causal contact. This raises a profound issue. If something can never influence us or be observed by us, does it meaningfully exist within science? Some physicists argue that if a theory predicting such regions also makes accurate predictions within the observable universe, then those unseen regions are legitimate consequences of a theory. Others argue that untestable domains belong more to philosophy than physics. Beyond the observable universe lies a boundary not only of distance, but of knowledge. The observable universe is defined by light travel time. But what if advanced civilizations billions of years from now look out into space? Due to accelerating expansion, they may see far fewer galaxies than we do today. Many distant galaxies will eventually cross the cosmic event horizon and disappear from view permanently. Future astronomers might conclude that their galaxy is alone in an empty universe. In that sense, we live at a privileged time in cosmic history, early enough to still see the vast structure of the cosmos. The question of what lies beyond the observable universe may never have a definitive answer. The boundary moves with time, but the total extent may remain forever beyond our reach. Yet the act of asking the question reveals something remarkable about human curiosity. From a small planet orbiting an ordinary star, we have mapped the cosmic microwave background, measure expansion rates, and infer the geometry of space-time. We cannot see beyond the horizon, but we can model it. Beyond the observable universe may lie endless repetition, or finite closure, or entirely separate realities. The true answer may remain hidden beyond the limits of light. But the horizon itself reminds us that reality is larger than what we can see, and that the universe, whatever its total size, extends far beyond the boundaries of our perception.